Welcome everyone to this another video about the OpenGL API. In the last part, we worked with the perspective projection and we had this output. So in this part, we're first going to work with some depth testing, and after that we'll learn about rotation. In this part, we will work with actual 3D objects. We will draw a cube instead of a square. So I initially had the geometry of a square here, which is drawn at the origin. So instead I'll use this geometry, these set of vertices which form a cube. So I'll replace this, I'll copy and paste this, and one more thing I need to change here is I need to use GL quads instead of GL polygons. So what quads does is that it turns four consecutive vertices into a single quadrilateral. So the first cluster of these vertices will become a single quadrilateral, which is a square. Similarly, the next cluster of 4 vertices will become another quadrilateral. So this is a way of drawing discrete quadrilaterals. If I instead use a GL polygon instead of GL quads, that means all of these vertices will form a single polygon, and that will not give us the desired output here of drawing a cube. So that will be something else. Another thing you need to notice here is that I've used separate color for each of the faces of the cube so that we can distinguish between the faces. I'll leave this geometry down in the description so that you can copy it from there, but I'll recommend that you try to make the cube yourself, and this could be an exercise to yourself. So one more thing you need to notice here is that the vertices of the front face are specified in the counterclockwise order, while the vertices of the back face are specified in the clockwise order. What that means is that so I'll start from the very basic. So a polygon or a quadrilateral, any geometrical figure, has a front face and a back face. So in OpenGL, if you specify the vertices of a quadrilateral or a polygon in counterclockwise sense, that means that the side from which you're looking at the quadrilateral while specifying it is the front face of the polygon or the quadrilateral, and the other face is the back face. So if you're specifying the vertices in the clockwise order instead, then that means the side from which you're looking is the back face and the other side is the front face. It is not relevant right now because we're not using the techniques that we're required to use when we'll learn more about OpenGL. Right now, both our front and back faces look very similar, but in further cases we might learn to use those techniques, and that's when we require the distinction between front and back face. But right now it doesn't matter, but it's always good to know which side of your polygon is front and which side is back. Here I've taken care while specifying this geometry that all the outer surface of the cube is comprised of only the front faces of all the quadrilaterals. So I've specified the geometry. One more thing I'll change here is that I'll comment this switch block. We will not use any animation so that you can have a good look at the geometrical figure that we get here. So that was all I was going to comment the switch block, and now let's try to imagine what kind of output we will get. So we're looking from the origin towards the negative z direction. Oh, I forgot to change this. GLTranslateF, I'll keep it at -8.0. So our origin will be here and our cube will be drawn around this point. So the output that we're expecting here is that we're looking from the origin towards the negative z-axis. So we'll see the front face of the cube, this face, which is red, and this will be the biggest because this is the closest to us, and this face will cover all other faces, so all other faces will not be visible. So we again expect to see a single red square on the screen, and let's see if we get that while running the program. So you can see there is something wrong with the output. We are actually seeing the green back face and the blue face and yellow, blue and the pink faces. The front face is not visible at all. What is the problem here is that we're not using depth testing. That means OpenGL does not know which face is in front of the other face. By default, how OpenGL works is that we specify this face, then we specify another quadrilateral. This quadrilateral is specified after this quadrilateral, so this quadrilateral will be drawn over this quadrilateral. It doesn't matter in 3D world which is behind which, so this is specified afterwards. So that means this will be drawn, back face will be drawn over the front face, no matter if it is in the back or it is in the front of that other face. So for to get real world like output, we need to use a technique which is called hidden surface removal. That means the surfaces at the back of a certain surface will be removed and the surfaces at the front will only be shown. That means the surface in the front will hide the surface in the back. So for that we need to use hidden surface removal, which is also called depth testing. So to start with depth testing, we first need to request a display mode which has special memory reserved for depth testing. So our display mode will also contain GLUT depth. So we have our memory for using the depth testing. Next thing we need to change is one more thing we need to enable. So we need to enable the depth testing using GL enable call. So this function GL enable will enable certain things. The thing to enable will be specified as the argument. So we need to enable GL depth test. So this means that we have now enabled the depth testing. One more thing we need to change. So for that we need to know that the depth testing is done using a buffer called depth buffer. So in that buffer, data about depth testing is stored for each frame, and that buffer is actually a part of the frame buffer. So similarly, like we cleared the GL color buffer bit, we also need to clear the depth buffer before every frame is drawn. So I'll add here GL depth buffer bit. So that means now the depth buffer will also be cleared with each frame. And now we have a full working model of depth testing, and now we can build and run our program, and we can now fully expect to see the front face in the front, and all the other back faces of the cube are hidden behind this front face. Now to see the back faces, we need to rotate our cube so that we can have a look at it from different angles. That is when we will actually see that our figure actually is three-dimensional. So for that we need to first learn rotation. So before I begin to explain how rotation works in OpenGL, let's first get familiar with some basic concepts of the rotational motion. So I hope you're familiar with the wheel and shaft model. So this is the wheel and this right here is the shaft. Assume wheel is spinning in this direction. So this point at which the wheel is connected to its shaft, actually the shaft is perpendicular to the plane of the wheel, so this point is stationary, this point does not move. So this shaft is called the axis of rotation of the wheel. Every rotating body has an axis of rotation along which it is rotated. So now let's assume this square, and now it will have its axis of rotation at this point. The axis is actually coming out of the screen and is perpendicular to the plane of this square. So coming out of the screen is represented by this sign. This is coming out of the screen and this is going into the screen. And you might ask that why does this direction matter, out or in, why does this matter? So I'll just explain it right here. So if the axis is coming out of the screen, then suppose I'm asking you to rotate the square by 30 degrees along this axis. So now what you'll do, you need to know that whether you have to rotate the square in clockwise direction or in anti-clockwise direction. So for that we use something called right hand rule. I'll explain this right here, but in case you're not able to understand it, you can Google it and you'll find diagrammatic representations on the internet. So to follow the right hand rule, you need to stretch out your thumb in the direction of the axis of rotation. In this case the direction is outwards, out of the screen, so stretch your thumb out of the screen and then Open your hand and try to curl your fingers inwards like you have to do while closing your hand. So you'll see that you have to curl your fingers in this direction. I think I forgot to mention you have to use your right hand. That's why it is called right hand rule. Thumb of the right hand stretched out of the screen and then curl your fingers inwards, so they'll rotate in this direction. So that means positive rotation is in this direction, while the negative 30-degree rotation will be this side by 30 degrees. So if I want to give it a positive 30-degree rotation, I'll rotate it by 30 degrees like this. So it was rotated from here to here by 30 degrees. So this was 30 degrees positive rotation when the axis is pointing out of the screen. Now let's assume the axis is pointing into the screen. Now while using the right hand rule, you need to point your thumb inwards and then curl your fingers. You'll see that they'll rotate in this side. So this is the positive direction of rotation. So positive 30 degrees will be, this will be rotated like this, positive 30 degrees up to here. So this will be the square after rotation. So this is how rotation is carried out in mathematics. Now let's move on to OpenGL. Let's assume this is our coordinate system in OpenGL. The x-axis, y-axis and the z-axis is coming out of the screen. So in OpenGL, actually you do not rotate objects. In OpenGL, the coordinate system is rotated. Like in the similar way like we translate the coordinate system to another point and then draw objects, here we'll rotate the coordinate system and then draw objects. The objects that have already been drawn, like I'll draw a square. I'll draw a square right here. It has already been drawn. Now I'll give OpenGL the command to rotate. So first, to rotate I have to specify the axis of rotation, which is a vector. So I'll specify the vector using the point 0, 0, 1, which is the positive z-axis coming out of the screen. So that means positive z-axis is my axis of rotation, and now I'll rotate it, rotate along this axis by 30 degrees. So after rotation, my coordinate system will become like this: positive rotation counterclockwise 30 degrees. This angle will be 30 degrees. This will be called x prime and y prime. So this new coordinate system, this is actually my new coordinate system, but the object like this square, which has already been drawn, will not be affected by the rotation. Now let's suppose this square was drawn at point 1, 1 and this was its geometry. Now in the new coordinate system, if I draw a similar square using the same geometry, it will be drawn at 1, 1 of this coordinate system, which will be here. So that's it. That's how rotation works in OpenGL. You have to first rotate your coordinate system. Actually, the coordinate system is rotated about the vector. The vector actually connects origin and the point specified by you to OpenGL. So let's have another example. Now what we'll do is I'll explain to you the difference when you rotate first and then translate, and translate and then rotate. What is the difference between these two cases? You have to keep both of these cases specially in mind, and you have to know which one to use first. So to see the difference, let's take a simple example. I'll take similar two coordinate systems, x, y, x and y. And now in the first coordinate system, I will translate to a point 1, 1, 0, and then I'll rotate along 0, 0, 1 positive z-axis by 30 degrees. So let's carry out these operations. So first, translating to the point 1, 1, it will be somewhere here. So this will become my new coordinate system, x prime and y prime. Now I'll rotate it along this axis by 30 degrees. So this will become my new coordinate system. I'll call this x double prime and y double prime. So this is my new coordinate system. This is final coordinate system. And now if I draw the square, at point 1 comma 1 according to this coordinate system. It will be drawn here. And now for the second coordinate system, I'll first rotate along 0 comma 0 comma 1 by 30 degrees, and then I'll translate to the point 1 comma 1 comma 0. So let's see what's the difference here. So I'll first rotate by 30 degrees. 30 degrees. This will be my new coordinate system, x prime and y prime. And now I will translate to the point 1 comma 1 comma 0. The point 1 comma 1 comma 0 will lie here. So this will be my new coordinate system, x double prime, y double prime. So you can clearly see the origin lies at different places. Here it is lying here, and here it lies at 1 comma 1. So these are both, this coordinate system is not similar to this coordinate system. So now if I draw the square here, it will be drawn somewhere here at 1 comma 1 of this coordinate system. So these clearly are different positions. If you see with respect to the black coordinate system, which was our screen here, this clearly is different for both of these. So that was the difference. And now what is our aim in this video tutorial is that to rotate the coordinate system in such a way that we can see some more than one faces of the cube that we have drawn, so that we get that 3D effect. So this is our current coordinate system, x, y, and the z-axis is pointing out of the screen. So what we'll do is we'll keep the axis of rotation as 1 comma 1 comma 1. The origin connected to the point 1 comma 1 comma 1 will be the vector of rotation, and we'll give it a rotation of about 60 degrees. So I cannot exactly depict how the coordinate system will look after this, but I can try a representative figure. So let's suppose it looks something like this after that. So if I draw the cube now, it will be drawn something like this. Some more faces will also be visible, and the different faces will clearly have different colors. So we'll now get that 3D effect like this. So this was our aim. This is going to be our aim in this video tutorial. So let's now move on and see how to implement rotation in the code. Now to implement rotation in OpenGL, we use the glRotate function, and this function has a suffix to it, which can be either f or d. F means that the values we are going to specify will be taken in as float, and d means double. So it has 4 arguments. The first argument is the angle. All 4 of these are actually float values. The second argument is the x coordinate of the vector, and the third coordinate second argument is the y coordinate, and similarly the third argument is the z coordinate. And these three coordinates, specify the direction of the vector along which the rotation will take place. So here you can see that we have translated to this point, to the point -8 on the z-axis, and this is our actual coordinate system. Here the origin is a bit far away from the camera on point -8, so that we can actually see the object when it's at the center. So after we have translated to this point, we'll rotate the coordinate system along a vector 1 comma 1 comma 1 by 60 degrees. So we'll use the glRotatef function, and the angle will be 60 degrees, and the x, y, and z coordinates of the vector 1, 1, and 1. And now I'll build and run this program, and this is my output. So you can clearly see that the 3 different faces of the cube, and now you can actually see that it's not a square, it is a cube, and you can see the various 3 faces, and it appears 3-dimensional. Now to have a better look at it, I will animate it. I will keep changing this angle right here for each frame. So I had these 2 variables here. I'll actually remove the state variable because I do not need this anymore, and the variable x position will now become angle, and I'll replace this here by angle. And now we need to increment the angle periodically. So instead of this switch block, I'll add the code angle plus equal to 0.8. I'll increase it a little bit for every frame, and this angle is in degrees, by the way, if you were confused. So if the angle becomes greater than 360 degrees, then I'll so that it does not overflow, I'll just make it start it from 1 again. So I'll write the code: if angle is greater than 360.0, then angle equal to angle minus 360.0. so that means if the angle, suppose it becomes 361 degrees, so this code will be executed and the angle will become 1 degrees. So that is it'll start from 1 all over again. So we have our code, and let's build and run this. So you can clearly see the cube is now rotating. The speed might appear quite slow. I'll try to increase the speed a bit. There is the speed. I'll make it 4 times. I'll multiply this vector by 4. Now I'll build and run it. You can clearly see the speed of rotation has increased. And we know the axis of rotation is actually a vector pointing from origin to 1, 1, 1. So to have a better look at it, I'll do some random rotation. So for that, instead of rotating along a single vector, I'll first rotate it along this 1, 0, 0, and then I'll rotate it by the same amount along a different vector. Then again this. You can see the rotation is a bit random now. So that was it. That was rotation in OpenGL. Now I need to add a final point here so that you're not confused in any way. So just like rotation and just like translation, rotation is also wiped out when the next frame is drawn. Like I have to translate to this point for every frame. Similarly, I have to rotate to this frame, rotate to this point for every frame. It works just like translation does. So that was just in case if you were confused. So that was all for this video. So I'll see you next time.